You're listening to Major Gazer. I'm your host, Callie Cross. Tonight we're looking at Jupiter's gravity well and how one planet's massive pull has quietly cleared our solar neighborhood of threats. There is a story about Jupiter that gets told so often it has become something close to received wisdom. Jupiter is our guardian, a gentle giant standing watch at the edge of the inner solar system, using its enormous gravity to swat away the asteroids and comets that would otherwise find their way to Earth. We owe Jupiter our existence. The story is clean, intuitive, and deeply appealing. It is also, at minimum, incomplete. And the part that is missing is genuinely strange. Here is what we actually know. Jupiter is massive, more than twice the mass of every other planet in the solar system combined. That mass generates gravitational pull that reaches deep into the asteroid belt, the band of rocky debris sitting between Mars and Jupiter. And within that belt, there are gaps. Observable, measurable, specific gaps where almost no asteroids exist. They were identified in the 19th century by an astronomer named Daniel Kirkwood, and they bear his name, the Kirkwood gaps. They are not random. They occur at precise locations where an asteroid's orbital period would fall into a simple ratio with Jupiter's own orbital period. 3:1, 5:2, 7:3, 2:1. At those resonance points, Jupiter's gravity tugs on any asteroid repeatedly, in the same direction, at the same point in each orbit. The cumulative effect is destabilizing. Asteroids in those zones get flung out. The gaps are direct observational evidence that Jupiter's gravity clears material. That part is not in dispute. NASA's Dawn spacecraft spent years orbiting the asteroid belt's two largest objects, Vesta and then Ceres, and returned data consistent with long-term gravitational sculpting on an enormous scale. The belt's total mass right now is estimated at roughly 4% of the Moon's mass. 4%. Models suggest the original belt was far more massive, and that the depletion happened because something was doing the clearing. The gravitational fingerprints point to Jupiter. Then there is the Grand Tack hypothesis, developed by Kevin Walsh at the Southwest Research Institute and published in peer-reviewed form roughly 15 years ago. It proposes that Jupiter did not always sit where it sits now. Early in the solar system's history, Jupiter migrated inward, potentially reaching a distance from the Sun roughly equal to where Mars is now, before Saturn's gravity pulled it back outward. That inward then outward sweep would have torn through the primordial asteroid belt, removing enormous quantities of material. The Grand Tack model is not consensus. There are competing frameworks, including the Nice model, developed by researchers at the Observatoire de la Côte d'Azur in France, which tells a related but different story about how the giant planets reached their current orbits. The science here is genuinely still contested between competing models, but the broad picture of Jupiter having profoundly reshaped the inner solar system's debris field is consistent across them. The most visceral piece of evidence for Jupiter's interception role is something that was actually observed. Comet Shoemaker Levy 9 was discovered in 1993, already in fragments, pulled apart by a previous close pass with Jupiter. In the summer of 1994, over the course of 6 days, 21 separate fragments impacted Jupiter in sequence. The Hubble Space Telescope watched it happen. Ground observatories around the world watched it happen. The largest single fragment produced a fireball, estimated to be larger than Earth. Jupiter did not just perturb that comet. It captured it, shredded it, and absorbed it directly. That is a dramatic, real-time demonstration of what Jupiter's gravity can do to a solar system body. So, Kirkwood gaps, Grand Tack, Dawn mission data, Shoemaker Levy 9. The case for Jupiter as shield seems airtight. Except, planetary scientist Jonathan Horner and colleagues at the University of Southern Queensland have been quietly building an evidence-based argument that the shield narrative is, at best, only half the picture. Here is the part that rarely makes it into the popular coverage, because it requires one more step of explanation that most articles skip. Jupiter does not just fling things outward. Its gravitational resonances can fling material inward as well, toward the inner planets, toward Earth. The same mechanism that clears the Kirkwood gaps can also perturb asteroids into Earth-crossing orbits, depending on the specifics of the interaction. And Horner's modeling work, published across multiple peer-reviewed papers, suggests something that sits uncomfortably next to the standard story. In some configurations, a solar system without Jupiter, or with a smaller Jupiter in a different position, might actually produce fewer impactors reaching Earth, not more. That is not a fringe claim. It is peer-reviewed work that appears in the planetary science literature and gets cited in subsequent papers. What it establishes is that the relationship between Jupiter's mass, its orbital position, and Earth's actual impact rate is non-linear. More Jupiter does not simply equal safer Earth. The math is more complicated than that. There is also the Nice model's implication to sit with. If Jupiter and the other giant planets underwent a period of orbital instability early in their history, as the Nice model proposes, then that instability would have sent large numbers of objects cascading into the inner solar system. Some researchers connect this to the Late Heavy Bombardment, a hypothesized spike in impacts on the Moon and Earth roughly 4 billion years ago. If that connection holds, then Jupiter's dynamics were once a source of dramatically increased bombardment, not a shield against it. And the Late Heavy Bombardment itself is now an active area of revision. Recent analyses of lunar samples have led some researchers to question whether the impact spike was as sharp and distinct as originally interpreted, or whether the cratering record was being misread. The question is genuinely open. So what we have is a situation where the most popular story about Jupiter, told in documentaries and science articles, and probably your middle school textbook, is supported by real evidence, and also challenged by real evidence. And the scientific community is actively working out which picture is more accurate. That is not a failure of science. That is what science in progress actually looks like. It is less photogenic than a giant planet heroically catching comets, but it is more interesting. The 1 million asteroids ejected figure that circulates in popular coverage is worth noting here. It appears widely, but is not traceable to a single named study with a defined methodology. It is plausible as a rough order of magnitude illustration of long-term belt depletion. It should probably be understood as a vivid approximation rather than a measured count. The broader claim it represents, that Jupiter has cleared enormous quantities of material from the inner solar system over billions of years, is well supported. The specific number is doing more work rhetorically than the data strictly supports. The honest, open question at the center of all of this is, has Jupiter, integrated across the full history of the solar system, reduced or increased the number of large impactors that have hit Earth? The answer is not settled. It depends on which population of objects you are counting: main belt asteroids versus long-period comets from the outer solar system, and on the exact parameters of Jupiter's orbit and mass. Horner's work suggests those parameters matter enormously, which means the answer could be different for a Jupiter slightly more massive or slightly closer in, or in a less circular orbit. What we can say with confidence is this: Jupiter is one of the most consequential gravitational forces in the history of Earth's impact record. What we cannot say with confidence is whether that influence has been, on net, protective. The shield narrative is real enough to be worth taking seriously. The threat narrative is documented enough to keep the shield narrative honest. And somewhere in the gap between those two, in the contested models and the reanalyzed lunar samples, and the nonlinear resonance dynamics that most coverage skips over, is the actual story of how Earth ended up with an impact history that made something like us possible. That story is still being written, and the scientists working on it have not agreed on the ending yet. That's Major Gazer. Thanks for spending some time under the sky with me. See you out there.
Grab news. Thomas.